Swayam Prabha. Digital India. Educated India.
Okay, so in the previous lecture, we spent quite a bit of time in trying to understand the various trends of proton and carbon NMR. So now what we'll do is we will spend some time and try to understand the effects of or the NMR pattern of benzene. So we will be spending quite a bit of time on aromatic compounds in this course, and therefore it's quite useful. Okay, so just to recap, benzene, basically is 3 pi bonds in a hexane ring, and so the orbital picture is going to look something like this, right? So you have basically p orbitals which have 6 pi electrons. So now the to understand this the picture, let's now look at the energy levels of benzene. So we have already seen that the molecular orbital picture is going to look something like this. So here are the bonding orbitals and here are the anti-bonding orbitals. And now if you fill in electrons, so you have 2, 4 and 6 electrons, and so these are the anti-bonding orbitals and these are the bonding orbitals, right? Now, so you have 6 pi electrons in the system and they are delocalized. Okay, so from an NMR standpoint, what we want to understand is that when there is a magnetic field that is applied, so there is an applied magnetic field. Okay, so when this magnetic field is applied, magnetic fields are nothing but magnetic fields are produced by circulating electrons. So if you remember, we had looked at the example of hydrogen atom, and we found that there are electrons that are going to be circulating, and therefore there's going to be a magnetic field that is produced by the electrons, which contributes to the shielding and deshielding, for example. Okay, so the greater the shielding, the nucleus experiences less of the magnetic field. Okay, so now in the case of benzene, it's very interesting because benzene has 6 pi electrons as we discussed it. So what happens is that these are the electrons that are going to be shown here. Okay, so when the magnetic field is applied in these delocalized electrons, what happens is that it produces a local field. Okay, so a local field, magnetic field is established, and this local field does two things. Okay, so it does the following things. So basically I'm not drawing out the hydrogens here, but it's obvious that there is a hydrogen, and this local field basically is called as the ring current. As the name suggests, it's a current that is produced in the aromatic ring. And so this ring current leads to a very peculiar situation where you have a local field that is going to be produced. Okay, so now in this local field is what it does is that it does two important things. One thing is that it produces an additional layer for for benzene, and so what it does is that inside the benzene ring, the induced field opposes the magnetic field. Okay, and outside the benzene ring, the field reinforces the applied field. Okay, so I'll repeat it. So it does two things. One is that it inside the benzene ring, that is here inside the benzene ring, it opposes the magnetic field. So opposes magnetic field inside the benzene ring. Okay, so this is what it does. Okay, whereas outside the benzene ring, what it does is it reinforces the applied field. Okay, so in other words, what happens is that you have a situation where the electrons are going to have two different effects on depending on where the hydrogen is placed. Okay, so you may recall that when you compare the chemical shift value for an olefin, so this hydrogens versus these hydrogens, okay, or any of those hydrogens, the chemical shift value here is about 5.68, okay, and whereas here it is 7.27, okay. So this is a very significant difference that is between these two numbers is really significant. It's huge, okay. So therefore, this difference in aromatic ring is attributed to the ring current effect that is prevalent only in aromatic rings. But what happens is that it's a very peculiar effect in that it only affects the hydrogens. So the carbon, for example, if I look at the chemical shift of this carbon, it is 127.2. Okay. And whereas this carbon here, the chemical shift value is 128.5. Okay, so if you see here, there's not really a whole lot of difference between 127 and 128. So the effect, the ring current effect, or the aromaticity effect in benzene ring is localized, or is primarily it affects the hydrogen atoms. Okay, so that's very important to understand, because the carbon 13 on the other hand is not affected. Okay, so I'll repeat this. So when the benzene ring is placed in a magnetic field, there is an induced magnetic field that is present, and leads to what is known as a ring current, and this ring current produces a local field, and the local field, it has a uneven effect. The hydrogens that are inside, or the groups that are inside the benzene ring, lead to opposition of the magnetic field, whereas the ones that are outside lead to a reinforcement. Okay, so therefore the outside values are more deshielded and they lead to a larger delta value. Let's look at some examples of various benzene ring containing compounds, which are basically substituted benzene rings. So as we saw, just for regular normal benzene itself, the chemical shift value is around 7.27. Okay, now what we're going to do is we're going to put in two nitro groups. Okay, so these are, and we'll understand why we are doing this substitution a little bit later. But these hydrogens, for example, when you look at the chemical shift value of this shows up at around 8.48. Okay, so how do we understand this? The way we understand this is that if you draw out the nitro group, such as shown here, okay, so if you draw out the nitro group, and if you pull these electrons over here, this is going to give rise to a resonance form where you have double bond NO minus with a positive charge, and this hydrogen here is going to be next to a electropositive NO2, right? So what happens is that because it's an electron withdrawing effect, the electron withdrawing group makes it more deshielded. Okay, so as you remember from the previous examples, anything that removes electrons from the nucleus is going to lead to more deshielded. So therefore nitrobenzene is more deshielded when compared with benzene. All right, now as we do a few more examples, these concepts will become much clearer. So now the next example we're going to take is cyanobenzene. So cyanobenzene, or benzonitrile as it's called, C triple bond N, C triple bond N. Okay, so as you can see here, this triple bond is very nicely placed to pull electrons, and so you can draw out a resonance form over here where, so you have double bond C, double bond N, and then you have a negative charge here, and it leaves a full positive charge here, and the remaining molecule is the same. Okay, so what it does is, again, this is an electron withdrawing group, and therefore the electron withdrawing group is going to make it more deshielded. I'm sorry, I forgot to tell you the chemical shift value. So the chemical shift value is 8.10. Okay, so clearly the nitro has a stronger electron withdrawing ability when compared to cyano, and so cyano has a slightly lower value in comparison with the nitro group. The last example we're going to look at is this compound which has CF3. Okay, so CF3, as you may know, the fluorine is highly electronegative. There is no possibility of a resonance-based effect, so this is going to be completely an inductive effect. And the chemical shift value of this hydrogen here is 7.78. Okay, so let me just rewrite that. The value is 7.78. Okay, so this value again is much greater when compared to benzene. So the CF3 definitely has a significant effect. Now let's move on to a couple of more examples in the halogen series. So let's look at, I'm just going to draw out the compounds as X and X. So when X is fluorine, then you can look at chlorine, bromine, and iodine. Okay, and what we're going to do is we're going to list out the chemical shift value. Okay, so the value for fluorine is 7.00. Okay, and that for chlorine is 7.24, bromine is 7.32, and iodine is 7.40. Okay, so if I look at these three substituents, it seems like these values are either, for chlorine it's comparable with that of benzene, but bromine and iodine are definitely more deshielded. Now when it comes to fluorine is very interesting because fluorine is the most electronegative atom, but having three lone pairs, fluorine can also donate electrons by resonance. Okay, so it makes it a weakly electron donating group by resonance, but a strongly electron withdrawing group by induction. Okay, so therefore this balance leads to this kind of a shift here, where fluorobenzene is actually going to have a lower chemical shift when compared with benzene. We'll also look at this later when we are looking at selectivity in substitution reactions. Okay, so next let's move on to a few other substituents. So the next substituent we're going to look at is toluene, okay, or CH3 in para positions. So here the value is 7.03. Okay, then I'm going to just draw out a general structure, and then we'll look at the trend X. So this 7.03 is again can be rationalized because this methyl group is weakly electron donating, weak EDG. So that's going to lead it to a more shielded situation, and therefore the hydrogen is going to be coming at lower chemical shift values. Okay, so now let's look at a few more examples, and we'll then sort of wrap up this lecture. Okay, so the next compounds that we're going to look at are basically again 1,4 substituted just for simplicity. So I'm just going to call this as X and X. Okay, so the first example that we will look at is X is, and we're going to look at chemical shift. X is methyl group. So if there are two methyl groups at the 1 and 4 positions of benzene ring, the delta value is 7.03. Okay, so this value is again lower than that of benzene, and one can understand this by the weakly electron donating effect of methyl group. The next example is OMe, that is OCH3. So OCH3 group, the methyl group itself is electron donating, but there is an electronegative atom right next to it. So what we would expect is that there's going to be a little bit of the oxygen is going to dominate. But oxygen itself is very interesting, because if you see the sort of situation with respect to oxygen is that you have a lone pair. So you have OCH3. So the electronegative atom is going to be pulling electrons, whereas the oxygen, being electronegative, can also donate electrons. So there is going to be, again, just like fluoro, there is going to be a balance between electronegative and electron withdrawing effect and electron donating effect. And here, in this case, the electron donating effect dominates, and therefore this becomes more shielded, 6.80. All right. The next example that we're going to look at is phenol. So when you look at phenol, or 1,4-dihydroxy benzene, as shown here, so what we're going to look at is the because of the oxygen, it can do two things. It can donate electrons, and it can also pull electrons. So when you look at OH at this position, the value is 6.59. Okay, so as discussed, oxygen can donate electrons through resonance but withdraw electrons by induction. And the last example that we're going to look at is 1,4-diaminobenzene, and here the value is 6.35. So clearly the electron donating effect of the nitrogen dominates. So if I have to describe this, the effect of nitrogen is mainly by electron donation. Okay, so therefore this becomes a very useful sort of guide for us to understand how aromatic rings are being affected by both electron donating as well as electron withdrawing groups, and the nature of the group can determine whether it's an inductive effect or a resonance effect, and depending on the strength of it, the chemical shift can vary.